Combining what we know about strain gauges now and the Wheatstone bridge interface circuit, we have a number of bridge circuits, different kinds of bridge circuits that we use for measuring strain based on the portion of the bridge that's used for strain sensors versus the portion used for normal resistors. So in this case, for example, I have a single strain sensor that's measuring some strain epsilon 1, and then the rest of the resistors are normal resistors. And we call this a quarter bridge circuit because a quarter of the 4 resistors in the bridge, only one of them in this case, is taken up by a strain sensor. Now when I have 2 of those taken up by strain sensors, in this case one strain gauge measuring strain 1, one strain gauge measuring strain 2, this is a half bridge circuit. And I'll go through a quarter bridge and a half bridge in this video lecture. And then in the case where we have all of the resistors in our bridge replaced by strain gauges, I have what I call a full bridge circuit. And that one's analyzed fairly similarly to half bridge, so I'm not going to go over that right now. So for the quarter bridge circuit, I'm going to assume all of the nominal resistances are R. And in the case of the strain gauge, I'm going to have an R plus a delta R, where that delta R is depending on the strain currently being applied to this strain gauge. And I'll have a V in going in as a supply voltage on my bridge, and I'm measuring a V out here. So I know from my earlier bridge analysis, I'm going to get a V out over V in that's equal to delta R over 4 plus 2 delta R over R. So I took the original analysis that we did and divided everything by R. Right, so this is the output. So if I multiply both sides by V in, I'd get my V out is this expression times my input voltage. And we had a nice simplification here. If delta R was very small with respect to R, so effectively delta R over R is a lot less than 1, then I could say my V over VI was approximately delta R over 4. So in this case, I'm saying this term down here is very small in comparison to this term, so I'm ignoring it. So I just get this delta R over 4. And then I know in my strain gauge, so for the strain gauge over here, I'm going to have my strain is equivalent to my gauge factor times delta R over R. So I can use this to substitute in. I can also write this as delta R over R is the gauge factor times my axial strain here, and I'm going to plug this in up here. So ultimately in this circuit, I'm going to get an output over an input that's equal to my gauge factor times my strain divided by 4, or multiplied by 1/4. So the response of this quarter bridge is nominally nonlinear, right? Because I have this kind of complex function of delta R over R, or if I plugged this in my strain. But I can kind of linearize it, and this is a reasonable approximation. If delta R over R is much less than 1, that happens a fair amount of the time. And if I linearize it, I get this output over my input voltage, or I can think of this as my output voltage, is going to be my input voltage times the gauge factor of my strain gauge times the applied strain times 1/4. And you'll see this 1/4 corresponds to the quarter bridge. In the half bridge, I have 2 of my resistors replaced by strain sensors. So a full half of the bridge is taken up by strain sensors. And I'm going to use, once again, I'm going to assume everything has the same nominal resistance. But in this case, I have a delta R1 based on some strain 1 that's applied to that first gauge, and an R plus a delta R2, which corresponds to the epsilon 2 applied to that second gauge there. So we're interested in how the output voltage of the circuit behaves as we have these small changes in the resistances of this circuit. And to do that, I can go back to my original derivation for what the output of this circuit is, which is the voltage divider on this side minus the voltage divider output on this side, all of that times the V in voltage that I have applied to the bridge. Now, in this case, I'm interested in how this output voltage changes with small changes in the resistances. And so I'm going to look at those small changes in the output voltage. And that's going to be the derivative of that output voltage with respect to, in this case, the first resistor times a delta R1, right? That small change. I could also write that as the capital delta there. In this case, the R1, and then I'll do that for each of my resistors in this bridge circuit. So R2. Now in this case, my R3 and my R4 don't have DR3s, those are 0, so these effectively are going to go away. And what I'm looking at are these two right here. And for those two, I'm going to use the knowledge that my delta Ri over Ri is equal to the gauge factor times my strain for that ith resistor, for that ith strain gauge. And so this all comes together to give me an output voltage that's going to be based on the two strains that I have, my strain 1 and my strain 2. So strain 1 minus strain 2 times my gauge factor over 4. Right? So if I do this math and I plug this in, I'm just going to get this now. And this is completely linear. I don't have to worry about any of those weird nonlinearities I had with the quarter bridge, right? And I'm just looking at the difference of these two strain gauges is going to give me my output. Oops. Times my VN here as well. Let's look at a quick example of that half bridge strain gauge. In this case, I have a cantilever beam, and I have one of those strain gauges on the top of the cantilever beam and one on the bottom. So this top one is going to be undergoing tensile strain, so that'll see a plus epsilon. The bottom one is compressive strain, so that will see a minus epsilon. So if I plug all of that into my equation, I'm going to get the gauge factor over 4 times my first strain minus my second strain times my Vn, and this will equal my gauge factor over 4. I can plug in these, so I have epsilon minus negative epsilon, so these will add together times Vn, and I'll get a gauge factor over 2 times my strain times my Vn. So now one of the key things to note here is now I have this 2, right? Remember in the quarter bridge circuit I had a 1 over 4 term. Now I have a 1 over 2 term. So I've improved the sensitivity of my sensor plus the bridge that was connected into.